professor of applied probability at the Faculty of Mathematics in Duisburg, Essen, and he's well known for his research in mathematical statistics, stochastic algorithms, and stochastic optimal control. And his main, field of applications lies on finance, computational finance, and various areas in engineering. So please, if you can share your screen, then we will see.
Let me see, 1 minute. I need to find the right file. I think this is the right one. So not completely clear. Difficult to resume. Wait 1 minute. Now this here. Okay, hello everybody. My name is Denis Belomestny, and I'm going to present my joint work with John Shormakers and Christian Bender. And this is work on stochastic average approximation and randomization. So I changed a bit the title, but in principle it's more or less what also written in the abstract, and that's a bit more general. But because I'd like somehow to draw your attention to possible extension of this approach, and in our current paper it was applied only to optimal stopping problem, but it turns out that it's quite general and can be also applied to other problems where stochastic average approximation is used. And this is the outline of my talk. So I will introduce the method of stochastic average approximation, then give some examples, then consider convergence, study convergence rates, and then I will introduce a Bernstein condition, which is quite important in my talk, and also consider, variance penalization as one approach to improve convergence rate for stochastic average approximation. And as a main novel approach, I will talk about randomization as a kind of alternative to variance penalization. And I will show also at the end some numerical results for optimal stopping problem, basically. Okay, so let us start with stochastic average approximation. This is the general approach to compute expectations of some complicated processes, complicated quantities, stochastic quantities, and here I consider a kind of general fields, random fields on some probability space. So what does it mean, field? what is the difference between fields and random variables. So basically, the argument here of this stochastic process is psi, which is a element of some functional space. So in general, okay, you know the stochastic process in the standard usual sense. This is process. This is a sequence of random variables somehow parameterized by time. And here you parameterize these random variables by some elements from a general topological space psi, which could be kind of functional space, or maybe a reproducing Hilbert space, or something like this. It's not so important at this point, but what is important is that we are going to study this optimization problem. We optimize, we'd like to find the solution of this optimization problem. So infimum of expectation of Z over psi. And the usual standard approach to compute these expectations is a stochastic average approximation method, which is somehow sometimes also called Monte Carlo method, or Monte Carlo optimization based method, or simulation based optimization approach. There are different names of the same more or less method. And how it works in general, I mean, the idea is very simple. You replace your expectation by its numerical approximation. And in this case, I will replace it by the stochastic average approximation, Monte Carlo sample, Monte Carlo average. And yes, and then I consider this approximated optimization problem, which I will solve by some methods, say gradient-based method or some another method, and then I will somehow study how phi is the solution of this average approximation to the original, to the Q star. Yes, so I will be interested in the closeness of the values, not of the solution themselves, but of the values. So, okay, I will need to formalize it a bit, because then it would be simpler if I work with some formalization. So basically, I will consider this product probability space to define all these samples on this probability space. So these random variables, this product space are basically this Monte Carlo paths of this process Z, and then I will introduce this approximated, this SAA approximation of the original problem, where I am optimizing Qn instead of Q star, and Qn is this average, which is usually called stochastic average, yes, or Monte Carlo average. Then what I can do next, if I computed this, I can consider an approximation for Q star based on a new sample, new independent sample drawn from this Z. So I would like to straight at this point, this is quite general type of process, because here the omega is element of our probability space, so it may have very complicated structures. This process is also, and this is not because I like this complications or this complex structure, but because it's really, I need this kind of generic structure for examples also. You will see it soon. So, because in general, in statistics and machine learning, usually people consider stochastic processes, say, where you have kind of one random variable as an argument. So, one given random variable with given distribution as an argument of some deterministic function. But this type of optimization problem turns out to be rather restrictive in my case. For example, if I will study, I'm going to study optimal stopping problem, optimal control problem, and this is for me will be a rather restrictive assumption. So and this is the reason I put it in this more general framework. And this is okay. Now we have this approximation Q hat, and we can compare this approximation with Q star and try to analyze the convergence rates of Q star of Q hat to Q star. Yes, and this here we have two parameters: n, small n, large n, capital N, where capital N basically is the number of these independent paths used to evaluate the estimated size, so to say, the estimated element which optimizes this, and small n is the number of, so to say, paths used to find this psi. Okay, this is a kind of general structure. Now, example. So, in principle, I will be interested in this general class of examples, which you can call min-max problems. So, this is a kind of basic example in my talk. So, we consider process Z, random field, which has this structure. So, we have, say, a number of fixed random fields, and then your random field Z is a maximum of these random fields. So these random fields, I will call them basis near random field Z. They could have a simple form than the Z itself, but I mean, then we take maximum, and then this is what we'd like to minimize, basically. Not this, but expectation of this quantity is going to be minimized. So one example, concrete example of this is an optimal stopping problem in the dual form. So optimal stopping problem basically is a problem of finding the optimal stopping time, which maximizes the expected reward, where you can see, okay, it's very popular in financial mathematics, also in machine learning, more general form of optimal control problems, Markov decision problems. But the structure in the dual, this optimal stopping problem is a dual form, can be formulated like this. So this is equivalent formulation. And now we optimize, we minimize over set of martingales, adapted martingales. And here you see this maximum structure. Yes, you have maximum of some random variables. Basically, you have exactly here this min-max problem here. Of course, this class of martingales is very large, and also, I mean, you need to, in order to solve this problem in dual form, you of course need to restrict yourself to some subset of this family of all adapted martingales. For example, you can take something like a kind of parametric family of these martingales. I will return to this in a minute, but in general, if you have some set M, you can try to solve this problem using SAA approach.
Denis, can I ask a question?
Yeah.
So in the formulation of the stopping problem, you have the random variable, I mean, the process set evaluated at this stopping time tau. When you go below, you have set I. Could you please
but tau
and I?
Yeah, tau takes values here below. You see here, tau takes value in the set 0 capital J. So in the set of natural numbers from 0 to J. And this means that basically this tau, big tau is a set of all stopping time with these values. In principle, it's clear you can upper bound this, but if you take maximum, put maximum inside of the expectation, it would be upper bound. But it turns out that you can also find an exact bound, not bound, but exact representation. If you say take not some particular martingale, but infimum over all martingales. And there is one martingale which solves this problem, which is called Duke martingale. Also, there are other martingale, but this is martingale is very popular, famous, so to say. Sometimes it is a unique solution, but in principle, yes. So this is a kind of, you replace this problem, which is also difficult to solve because in general, you need to, if you consider this as an optimization problem over stopping time, this is the kind of infinite dimensional optimization problem. This is also infinite dimensional optimization problem, clear, and but if you say make kind of finite dimensional approximation, say for M, you can solve this problem using SAA approach. So this is the idea, and how it looks like. So for example, suppose we have a family of martingales, which is parameterized by psi, which is an element of some metric space. Then you can consider this random field, Z omega psi, which is somehow also depends now on psi, which is element, which is somehow element parameterizing one element of the psi, big psi, capital psi senses. So now you can apply this approach. Of course, how the main question is how to choose this martingales, family of martingales. And one usual, or so to say, simple approach is to consider a linear combination of some basis martingales. So you can say, I have K, capital K, some given martingales, and then I study, I consider all possible linear combinations of these martingales, and this is my family now. And I will optimize over coefficients psi1, psi k. This is now finite dimensional optimization problem. Key dimensions, we have the dimension of your space is capital K. And now with this, and this problem could be solved using linear programming, because this is the advantage of this parameterization, because this is a kind of linear programming. You can formulate this problem as a linear program. You can solve this SA problem. Yes, so basically you have here this SA average, yes, this Monte Carlo average, and then you optimize. But because of this maximum here, the maximum, it allows you to have this combination of maximum and linear structure inside the maximum, allows you to apply linear programming approaches. And so basically you can, and linear programming is known to be very efficient, and there are efficient algorithms how to solve it. And if we somehow focus on this type of problems, then the min-max problem of this type, maybe with some linear parameterization or maybe non-linear parameterization, then the main question is, what are the convergence rates and how they can be improved? Or, for example, how we can improve here. So I will not be really interested in the type of numerical algorithms, for example, used to solve this type of, for example, linear problem. But I will be more interested in analysis of this convergence, assuming that this problem, for example, linear programming problem, can be solved efficiently. So this is a kind of setup I consider here. And now, okay, what can we say about convergence of this SAA approach? For example, this Q hat, which we defined before, to the Q star. And there's several results from the theory, from statistics, from empirical process theory, which allow us to answer this question. And for example, if you say, if psi star, for example, a solution of the original optimization problem, one of the solution, not necessarily the unique one, but one of the solutions, then it follows from the standard results on empirical process theory that the order of convergence is 1 over square root of n. And this you can also find in the many textbooks, like the famous book of Shapiro, who studied this in details. And this is with high probability bound or expectation. Here, the high probability bound. So with high, because why high probability? Because your psi n is random. Yes, you don't need, you don't have to forget this. Always here in my talk, the psi n is random. Yes, it's based on samples which you generated. Yes, to somehow to solve this A problem. So psi n is really random, and therefore the left-hand side is random. And this is the reason why you have here O, some bound, but it's random. So it's you. So we can talk about high probability bound, and this will be throughout my talk. I will be always talking about high probability bounds, which are usually more difficult to get than the bound in expectations. By the way. Okay, now how these convergence rates are usually obtained? They are based on some concentration inequalities. What are the concentration inequalities? They're more or less the inequalities which show how fast your average approximation converges to the true expectation. And of course, they are always of order 1 with square root of n. This is well known. It follows from central limit theorem. But in order to get some kind of finite you need kind of concentration inequality. So you can use the concentration inequality. On the most famous concentration inequality, I think, is the Belomestny inequality, and this would give you the following bound. If, for example, your random field Z is bounded by constant H. So this is kind of standard bound, but it, of course, not sufficient for our purposes. Why? Because it is only for fixed psi, fixed function psi, not uniformly over class of psi, but only for one fixed. And this is not sufficient. What we really need to prove bounds on this stochastic average approximation, we really need uniform bounds like what you have here. So you, for example, it would be nice to have bounds like q psi minus qn psi divided by the variance of z psi, and this uniformly in psi. Why do you need this uniform bounds? Intuition is very simple, because you will, at some point, you will put here, if you compute all these errors, you will end up with some quantity which is qn of psi n. And because psi n is random, it's very difficult to say something about qn evaluated at psi n, because psi n depends on qn, and this. So you really need to have a kind of uniform bounds over all psi, and then you can somehow avoid this dependence and avoid this somehow this unpleasant randomness, and also inside of qn, which is also random. And so this is the reason why we need really some kind of uniform bounds. But this type of bounds are available in the literature, and this concentration bounds or Talagram inequalities is some famous cases of this. And for example, if you apply, I will not go into details here. This is the big theory well developed in statistics and machine learning. But for example, in this particular case, you can prove under some restriction on your class psi naught. And this will be always the case. You need some restriction on psi naught. So you need really some restriction on complexity of this class. If this class is too complex, too complicated, too big, then you will not be able to get any reasonable bound. But if it is small, in a sense which I will define precisely a bit later, but in some sense you can say this class is not big. Yes, and then in this case you can get, for example, bounds like this. Yes, so you can say that Q evaluated psi n, but Q, of course, this is here it involves the exact expectation, but evaluated at psi n, and he exact expectation evaluated psi star. That this bound, which is this difference, which is of course always non-negative, yes, because psi star is defined as a maximum and psi n is defined empirically, but it's always upper bounded by this quantity. And you see here, it goes to 0 as n goes to infinity, with the rate usually in general of order 1 over square root of n, because this term will be dominating. As long as q psi star is positive, yes. If q psi star is 0, for example, then or very small, for example, I don't know, 0 small, then the second term will dominate and you will get convergence of order 1 over n, which is of course is much better. And this is exactly what I like to investigate. Main question will be how to get this rate 1 over n, and not 1 over square root of n, because this is somehow important question for several reasons. Okay, first, okay, you can see this convergence also in numerical examples, yes, and but also important thing because it's how to choose parameters and what is the complexity of your procedure, yes, because then you need less samples. And so improvement is rather important. And you see here, okay, this is the usual rate is 1 over square root of n. But in some special cases, for example, if the optimal value at point psi star is 0, then you have a rate 1 over n. But this is, of course, very restrictive assumption. How can we do better in general? And there are several approaches to improve the situation. And all these approaches are more or less, they're based on the so-called Bernstein condition. What is Bernstein condition? Bernstein condition is somehow a condition of your process, this field, which relates somehow the norm of your L2 norm of your of increments of this process as a process in psi to the increments in expectation, increments of the expectation. So because basically what you have here, this is L2 increments, L2 norm of the increment Z, and this is the difference of expectation at the same points. And if you can bound your L2 norm by this difference, then people usually say that this process enjoys this Bernstein condition, fulfills this this Bernstein condition. And usually it's you can check it in some situations. Bernstein condition holds, and under these Bernstein conditions, you can prove that the rate will be 1 over n, not 1 over square root of n, but 1 over n. And but of course, this condition is not always satisfied. One must frankly say this is a condition which is usually not satisfied, but there are some ways how to modify the original problem, the original optimization problem, to get it satisfied. And how to, okay, what are these ways? What is these modifications? One modification is based on penalization, and the Maurer-Pontil 2009 proposed to add some variance penalization to the original, to this SIA objective function. So this is your SIA objective function. Basically, this is the empirical mean. And now you add empirical variance of the process Z. So this is basically Q is a expectation, empirical expectation, so average, but this is empirical variance of this Z. And it turns out that if you modify this objective function this way, then you can get better properties of your solution. And there's people, they proved somehow that you can get even the rate 1 over n in some cases. They prove the following theorem. So now you see the bound. Bound is similar form which we saw before. Now you have here psi n alpha, which is this penalized solution of this penalized optimization problem, variance penalized. And now you see here, if you look at this bound, what is important to see here is that you have 1 over n, second term, as was also in the previously, and we also have 1 over square root n term. But what is important that in the square root term, we have here variance of z psi star. So if, for example, your variance of z psi star is 0, so what does it mean? Somehow it's the optimal point, at the point of optimality, you have basically constant. The randomness disappears at the point of the optimality. Then the convergence rate is 1 over n. And this is somehow surprising, but it's somehow yes, it holds. Yes, and why is this case interesting? Why is this case variance z psi star is interesting, or say natural, as compared to the previous case where I mean the previous result is the optimal value at psi star. Assuming that the optimal value is 0 is very unnatural in my understanding, but assuming that the variance is 0 is much more natural. For example, if we go back to this optimal stopping problem and the dual form, then it is well known, maybe I will go to clarify this issue already here, that if, for example, the solution of this problem is m star, as I said, dupe Martin, one of the solution, and this solution will lead to this optimality here with probability 1. So basically, even without expectation. So if you put here something like m star, that this will be exactly equal to the optimal value, even without expectation. So almost sure. And this basically means that at the point of optimality, your variance is 0 because it is a constant. This maximum is constant. And this is one example where this assumption is fulfilled. This one, I mean, that the variance of this process is 0 at the point of optimality. Okay, this is not the only way to somehow to achieve this rate. But first, maybe about disadvantages of this approach. Okay, the main disadvantage of this approach is that penalized optimization problem, you can lose, some properties can be lost. Yes, for example, convexity or linear programming property. I mean, the property that is a linear program, because this penalization, if you look at this more carefully, it's somehow is kind of weird optimization, weird penalization, because you have variance square root, and this function is not even convex in psi, for example. Yes, maybe not convex. This is may lose convexity, and at any case will lose the property of this linear programming structure. If, for example, you go to this optimal stopping problem with a linear class of martingales, you will lose this linear programming structure. And this is a bit disappointing because it's, yes, the problem is difficult to solve numerically. Okay, but other ways to modify the objective function. Yes, there is another way, which is called robust SAA. What does it mean, robust? So basically here you really modify your objective function significantly. And as this approach works only this specific simple situation, which is quite popular in machine learning, where you have your process Z is kind of deterministic function of psi and a given random variable X, which has a distribution. P. Yes, somehow this is deterministic function, quite important. Yes, so your all randomness is inside of X. Yes, it's inside of X. And now you can consider their objective functions, the empirical objective function, which is called robust expectation, or it has different names, robust robust optimization, which is somehow based on the idea to optimize a bit over distributions here P. So now you move a bit from the distribution P. So you can see the kind of ball around your distribution P. I mean, around your distribution Pn, your empirical distribution. So basically, we have your empirical distribution, you have a sample, and now you consider ball in this measured in this where the distance is measured by this divergence. Yes, it's a so-called phi divergence. You can do it for different phi's, and as an example, you can get Kullback-Leibler divergence. One example. You might get also a different type of divergences, different type of metrics or distances here. But what is important, is you consider not all distribution P, but only a class of distribution which are somehow close to Pn. And this closeness is measured by the d phi, and it should be not phi divided by n exactly. So somehow, what is the difference between this problem and the original SAA problem? The main difference that you have here, by original SAA problem, you have here only one measure. This is Pn. So you optimize expectation with respect to your empirical measure. And here you allow to move a bit from the original, from the Pn, so to say, not original, from the empirical measure Pn, to move in some directions and to look a bit. And this is also called robust because you take kind of supremum over all possible P in this ball. Yes. So not only one P, but you consider, so to say, you can think about the worst case, so to say, in this ball. And it turns out that if you modify your objective function to this and consider and optimize now Rn over psi, then you can get better convergence rates. And I will call it psi n robust, which is a robust solution. And there is one result on this, not from me, but from other people, which say, okay, says that we can, the expectation of this value, L computed at this psi n robust is bounded from above by this quantity, and you see here you have here kind of trade-off between expectation of L, the true under true measure expectation, and you have here variance, and you can basically play with the psi, find psi which is minimizes this sum of these two terms, and basically important is this corollary. If, for example, you have again the situation where variance is 0, and this is psi star exactly solves this problem. So there is one solution of this problem where you have variance 0, then you again you can get the rates 1 over n up to some epsilon, which has higher order. You can see this from this because you can also here trade off between the probability, taking probability P large enough and epsilon. So it's more complicated structure. I will not go here into much details because then I will need to explain many things. But in general, there is a kind of this approach also leads to improvement on the rates, and also in some cases also you can get 1 over n rate. Although in expectation, not high probability, and also for the special structure of your process, so to say, where you have dependence on x, some random variables. So unfortunately, this optimal stopping problem in the form I presented, it does not fit into this framework, but I think that can be generalized a bit. I have not yet done it, but this kind of, I think this can be also generalized to this more general type of functional. These functions are usually called in statistical loss functions, yes, because they measure somehow the loss of your estimation if you estimate something. So they have special meaning in statistics, but here in our case, its meaning is simply kind of objective function for your SAA problem. Okay, this is the second approach, which is of course also good, but more restrictive than the first one. But it's good, for example, for one reason, because it retains some properties of the original problem, for example, convexity. So you can easily prove that if the original problem was convex, then this problem, so if L was convex in psi, for example, then this is Rn will be also convex in psi, which is a nice property, which can be somehow used it can be very useful. Okay, but there are also disadvantages, and one disadvantage is difficult to compute this quantity. It involves another optimization problem, yes, over these measures, yes. There are some efficient way to compute it, but still it's more complicated. Okay, this is what we have, these two approaches, and here I'm going to present, so this is state of the art, you can say, and I'm going to present a new approach to this idea, new approach, how to improve the convergence rate of SAA method. Is it based on randomization? So how it works? So basically, we consider now the process Z tilde. We fix a random variable psi independent of Z, and then consider maximum of psi and Z. So now it's a kind of, you simply take maximum of some random variable psi and your original random field Z. And crucial for this approach, the following theorem, yes. It somehow says if you now have a psi star, there's a point of the optimality, then the difference, so to say, this L2 norm of the increments of this process Z tilde is bounded above by this quantity where lambda mean is some number which depends on probability on distribution of psi. And now you have something like a difference of the expectation plus some additional terms. So it looks like a bit like Bernstein condition up to this additional variance term. So yes, it's because in Bernstein condition was exactly about this bounding the two norm of the increments by the difference of expectation at the same point. So this more or less Bernstein condition, which I introduced, but you have here variance, and also it's clear variance at the point of optimality is 0, then you have exactly Bernstein condition. And okay, this is about this quantity, but also what is important here is the bias, so to say, because by going to this Z tilde, we of course introduce bias, yes, bias term, because this maximum expectation of Z tilde is not necessarily equal now to the expectation of Z, yes, the original at the point of optimality. And therefore, this is important to somehow to assess this bias term, to estimate it. And there is a kind of bound also saying that, okay, this infimum of Z tilde expectation, this is of course larger than the expectation of the original process because we take maximum, but we have also upper bound that says it's almost equal to infimum of the original expectation of the original process plus some function of the variance again at the point psi star. And this function is unfortunately non-linear, but it has it's larger than 0 and is 0 at 0. but it's also continuous. It also can be proved, and this is I have exact form of this function, but it's kind of polynomial form. But anyway, what is important again, if variance is 0, then we have again that we have a nice property that we does not change the expectation by considering this maximum process, maximum science. And basically, this can be explained and somehow intuitively, because it can be explained. For example, if you put here psi star, this is constant, yes. And if psi, so to say, has some properties, the distribution has some properties. Yes, it's for example, it's concentrated on somewhere where your value of z at psi star also leaves, and then you will get this. You can prove this. So basically, in some sense, this means that this modification of your original problem is good if your variance is 0 or very small. Yes, at point psi star. And you can prove in this case, you can prove the following results. So if we now consider the optimization problem with this new objective function, this empirical SIA problem, then we can prove that the difference tilde, which is an expectation of this modified function, where is a maximum, yes, and modified function psi star is has the following order. So it is okay, there are some conditions which maybe I comment a bit later, but let me first go to the main result. So this q tilde psi n tilde minus q tilde psi star is bound by this quantity. Under this assumption, which I call somehow generalized Bernstein condition, where you have additional variance term. So basically, you have again this term 1 over square root of n presented here. You have 1 over n, and you have another term, which is somehow related through this parameter alpha to the complexity of your class psi. And now I go one step back and explain what is complexity here. The complexity here is measured using the entropy number or the covering number. So basically, this is n is the number of balls needed to cover your psi naught with respect to this metric d and radius u. So basically, you take, so to say, you ask how many balls in this space I need to cover this psi naught, and that such that the radius of each ball is not larger than u. And all is measured in this metric d. And here the metric d is given by this metric related to the increments of the process, the original process, not modified by the original one. And now if we say, okay, this is, of course, it's clear that this quantity increases, because if u becomes smaller, you need more and more balls to cover the space. And then the quite important quantity is the rate of this increase. That's how fast it increases in u. And here we can say this class is the logarithm of this increases polynomially. Yes, in so to say, in 1 over u. Yes. As this is a kind of usually in statistics, this is called non-parametric class. It's big, very big class, because you have that logarithm. That means that n itself can grow exponentially in 1 over u. And this is, so to say, non-parametric class. And this is one very important condition. And this alpha measures exactly the complexity of your class. Yes. The larger is alpha, the more complex is your class of psi. And another condition is condition on the moments of your increment process. So basically it says that this process, as you have exponential moments of your increments, yes, here. And the increments are somehow normed by this metric. And this parameter alpha is exactly what you see here in this rate. So rate depends on alpha, but for example, if you consider the classes which are smaller than non-parametric classes, for example, the so-called parametric classes. What does it mean, parametric? Here, parametric means that this quantity, this logarithm of 1 plus your covering number, this entropy number is growing only logarithmically, for example. In this case, people talk about parametric classes, and in this case, alpha is basically, you can take it 0 here in the main result, and you will get 1 over n here, 1 over n here, and if you additionally have variance 0 at point of optimality, you will get 1 over n rate. So this is somehow result which says, okay, and here we also took into account the fact that the bias is also 0 in this case, if the variance of psi star is 0. So basically you have this result, and but you can also put here, I written q tilde, it should be here basically q. You can also replace here q. You can write q for psi and tilde minus q psi star is for the 1 over n. So basically this is the main result, saying that by using this randomization method, you can improve the convergence rate to 1 over n. So this is a kind of main message to take out, that if you have a kind of variance 0 at the point of optimality, for example, as in this optimal stopping problem, then you can improve by randomization, you can improve the rates from 1 over square root of n to 1 over n. And this is a kind of so to say the main message here. Of course, the question is what happens if it is not 0, yes? If the variance is not 0 but small. But again, you can of course look at this general result and see what happens if your variance is not 0 but small. Yes, then of course it depends which term dominates here will depend on the order of your variance at this point. Yes, and this you can somehow find out what will be the leading term, but in any case, it's more complicated. And also an important issue is how to choose the distribution of psi. So you need that your psi, the support of your psi, I mean, if you go back to the definition of this modification, so you really need the support of your psi somehow contains this z at point psi star first. So it should be somewhere, it should be large enough. On the other hand, it should not be too large, because otherwise you will increase the variance, and also you will see that this constant lambda mean will also be large. Yes? So you need really a bit to somehow optimize over these distributions of psi, but in practice you will see this also. And this is one numerical example I would like to present at the end of my talks. This is stopping problem. It's Max-Call problem for geometric Brownian motion as a kind of benchmark examples used in many textbooks. Now we take psi to be gamma distributed with mean A and the variance B squared. And then we consider the family of martingales of this form. So you have many coefficients here. Basically, you have time increments. You have two families of martingales, not two families, but basically you have two martingales, only two martingales, but you have coefficients which are different for different time intervals. And this is what we call local martingales, yes? In the sense that we can, by choosing different psi's, coefficients of psi, we can somehow change locally the martingale. Yes? So only one increment will be somehow added with different weight to it. Yes? So we have here many parameters. Basically, in these examples, it will be j equal to 54, and so basically we have 108 parameters. There's quite a few parameters. and you need to optimize it. So we run a linear programming algorithm to solve this. And now we compare this, what happens if we randomize and if we don't randomize. And what we see, for example, at one picture, more pictures you can find in our preprint, which is on our archive. So basically you see here a very large deviation, yes, for the non-randomized problem. This is related to the fact that basically you always choose some martingale, some martingales from this family which have higher variance, yes. And because this randomization approach is similar in some sense to this variance penalization, in the sense that it also chooses a martingale with smaller variance. It prefers martingale with smaller variance. This is the reason why for randomized problem, we have much less variance. And this is in particular for this choice of a parameter, the gamma distribution. So A is 40, B square is 40, but okay, this particular choice for this, we also, it's for this problem, but I mean, in a sense, it's chosen in such a way that your support of your distribution contains this optimal value. But if you take it a bit different, this will not change much. They're rather stable, but you see here, the difference is very large. So basically, I mean, really here the deviations, the standard deviation are huge, yes, for non-randomized problem, and you achieve kind of, you can even think about variance reduction in this case, because it's, you reduce variance, but you will not introduce bias, and so didn't show, but it somehow is also, you can see that the bias will not be the value itself will not be changed much, yes, but the variance will be reduced significantly. This is again, this is the reason for this, is that this randomized approach chooses the martingale, chooses the coefficients that somehow minimize also the variance, yes, if you process it. And this is because there are, in these problems, there are maybe many possible combination of psi because of the high dimension, which lead to more or less the same value, but different variances. Yes, so there are some combinations of your coefficients which give low variance, and another coefficient give higher variance. But this approach will choose combinations with low variance, and this is somehow the reason. So this is all, and thank you very much for your attention, and I'm ready to answer the questions if there are some questions. Thank you very much.
Thank you, Denis. We have a couple of minutes for questions. So let's see if there's a question from the audience. Yeah, just a moment. Inside. Yeah.
Hi, Denis.
Hi.
Paul. Just a question, sort of for my understanding, maybe on slide 10, when you introduced this, the first convergence rates.
Do you mean this one? Oh.
No, maybe one more, maybe slide 9. Yeah, so yeah, slide 9.
I think the first convergence rate was here, more or less. Yes.
Yeah, this one I meant. So I probably think about this the wrong way, but I just want to understand why. So let's say I do the optimization one with n, and then I could rescale the objective function with that approximation that I have.
Yes.
Just by subtracting it and make then q smaller, right?
Yeah.
And then if I would optimize again, there's nothing changed basically for the optimization problem.
No, the value changes, yes, the value of Q, but here, of course, you need to, because here the sign shows that there are some hidden constants here, yes. So basically here also there's some hidden constants. So basically, if you scale your Q with some constant, you also be you will be, everything will be also scaled because there are some hidden constants here depending on Q, yes. I didn't show this because it's too big. If I will show all constants, it will be, not really clear. But the answer is only that if Q psi star is 0, yes, then you have order of convergence 1/n. But of course, you are right. If you scale Q, say multiply Q with some constant, and of course, there's this right-hand side should be also multiplied with this constant, yes.
No, I meant more, not multiply Q with a constant, but subtract Q with Qn, and then do everything again. That's what.
Subtract Q from Qn. Okay, and then, what will be your?
And then if I subtract Q with Qn psi n, so this is my approximated value.
Yeah.
And this is closer to 0, right? That's just what I meant.
But you don't know this. Basically, what is some procedure? You estimate psi n using your Qn, because psi n is a optimal point for Qn. Now you evaluate this psi n using, say, new sample, but what you see here is a Q, is a true Q. Yes, you evaluate your Q at psi n now. So I'd like to show how far is your Q psi n to Q psi star. This is somehow quantity you are interested in, but of course you can also consider different quantities of. But as I said, this is the first inequality what you have here. This is a kind of this is not the main. This is a kind of result which follows from the theory of empirical processes, because this is a kind of uniform bound. In order to estimate this, you need uniform bound Q psi minus Qn psi for over all psi. Yes, this is only to somehow to show this how to point to this problem that if you have psi n, which is random, which depends on Qn also, and then you, yes. This is
thank you. We'll talk tomorrow again, so I can ask you some more.
Yes, but
thank you.
Yes.
Okay, so thank you, Denis. Again, we are over time, so we have the next speaker.
Okay.
By schedule, we should have.
Thank you.
Hello.
Yeah.
Thank you very much. So
yeah.
we hope
we'll
be in touch, and we hope to see you here at some point.
Maybe in Aachen.
Take care, Denis. Maybe in Aachen. Yeah, vielleicht. Yeah. Okay.
Bye-bye.